Swayam Prabha. Digital India. Educated India.
So that is why we need a system which can give me an idea how the structure behaves in its solution structure. And for that, we have CD spectroscopy, which can give me a unique idea how many alpha helix I have, how many beta sheets I have from a solution. How to do that? So as we just said, before I do a CD, I need to do an absorbance spectroscopy first. Absorbance versus lambda. And over there, say I have a peak like this, and this peak generally look into 180 to 230 nanometer region. Every protein have a band over there, every protein, because this band is coming from the amide bonds. And as we know, amide bonds are actually present in every protein. This band will be always there. And with respect to that, if I now take a look into a CD spectra, how the CD spectra looks like. And here comes the data, how it actually looks like. That is how it does look like. So let me go through one at a time. So first, I look into the ellipticity, positive, negative. Don't look into the actual value now, look into the trend with respect to the lambda. First, if you have an alpha helix, you are going to have a signal like this, a very characteristic signal, so, same as the blue line over here. So you have a positive band around 193 nanometer. Then a negative band, it crosses and comes to negative, and in the negative region you have two maximas, one at 208 nanometer, one at 222 nanometer. If you have these three signatures, 193 positive, 208 and 222 double negative, you can say I have an alpha helix. For beta sheet, how it is coming? So for beta sheet, you have a positive band around 195 nanometer. Then it goes to negative. However, instead of double negative, you have a very broad peak, and the maxima comes around 218 nanometer. And if you have that, you can say I have a beta sheet. One positive 195 and one broad negative at 218 nanometer. And then if you have a random coil, that means not really oriented in a particular way, it starts with a negative value around 100, lower value, and then it crosses, and then it remains positive in the region between 210 to 230. Previously, which was in the negative region for both alpha helix and beta sheet, now it becomes positive. And there is no particular such peak, it is mostly slowly going down. The peak only found over here, 195 nanometer, but it is now in the negative region. If you have that, you can say I have a random coil. That means if you take a sample of only alpha helix, you should see a band 193 positive, 208, 222 negative. You say I have alpha helix. Beta sheet, characteristic peaks, 195 positive, 218 negative. Random coil like this. And it is going to give you the data in the solution. Now you can imagine that in a protein there is a mixture of alpha helix, beta sheet and random coil, right? So what you are going to get is a mixed signal. You are going to get a mixed signal in CD. This is absorbance spectra. This is CD spectra. I'm also looking to CD spectra now. And what you are actually going to get is probably something like this, which shows that you have a mixture of alpha helix and beta sheet. And you have the particular values, and from there, what do you need to do? You just need to do some deconvolution, where you actually try to get the original data and try to match up with some expected value. Say I have 70% of my alpha helix and say 30% of that is beta sheet. If they matches, then I can get this black color original data. So from there I can find out how much is my beta sheet and how much is my alpha helix. You can find out. And also you can find out how much is your random coil. And all those things you can imagine now, it can be done computationally. You have to just record the original data and feed that data into a computer and ask them to run a logarithm to find out how much is alpha helix, how much is beta sheet. And by that, you can figure it out what is the overall structure of a protein in a solution. And not only that, you can also figure it out what is the change happening in that particular molecule as you change the pH of the solution, as you change the temperature of the solution. And that will be directly affect the alpha helix, beta sheet, their orientation, and the CD spectra will change accordingly. So for an example, say I have a protein structure with only alpha helix, and I have a data like this. So in anywhere in your life you are drawing a graph, make sure that you always draw the axes and write the proper axes, like what are those axes actually mean. So in that, I see this particular data at say 298 Kelvin. Then say I change the temperature, I'm heating it, and slowly the same solution data looks like this. Then at one point of time, it becomes like this. That means what is actually happening as I increase the temperature, my alpha helix structure is going to a random coil. So what does it says? It says my protein structure is actually degrading. And if I can measure this particular data at different temperature and say I am monitoring what is the change happening at 208 nanometer and plot that with respect to temperature, how my data will look like. At 208 nanometer, I have a very negative value at 298 Kelvin. Then I go further temperature high and slowly it is going up. And at one point in time, it will remain same because at that point of time, you actually already degraded the protein. So from there, this point, I will say here, the protein is breaking down. And this is known as the melting temperature of a protein. Melting temperature means where a particularly nice helical structure with respect to temperature just defolded. And protein folding has a huge role to play with its function. So with respect to CD data, we can very easily find out exactly where does it happen. And if I want to do an experiment at which particular condition I should do where the protein structure is still stable. And after what, I can actually break it down. So what is the temperature I should keep my protein? So all this, for an example, right now we are looking into different vaccines, and some of the vaccines are protein-based vaccines. And over there, you can imagine that they always have to keep it at a particular lower temperature. Why? Because if you go to higher temperature, you can break down your protein structure and the vaccine will go bad. So how to look into that? How to find it out? Which temperature would be the safest for it? So you just do a simple CD spectra and find out where you see this melting point. And you can specifically point out this is the temperature you have to keep to make sure the protein is stabilized. Now, the last part I'm going to talk about.
Hello, sir.
Yes.
Sir, you showed in graph that alpha helix is changed to that upper one graph in random coil. But what about beta sheet?
Yeah, I'm just giving an example. It can go to a beta sheet. It can, all the possibilities can be there. Because I'm just giving an example that one alpha helix is going to random coil. You can think about, it can also happen sometime higher temperature can actually bring you to a totally new structure. It can go to alpha helix to a random coil to a beta sheet. And from the CD spectra, you can follow it up, like exactly what is actually happening.
Means after heating, beta sheet can be converted into random coil?
Yes, it is possible. All possible. So random coil is generally the structure at higher temperature because it doesn't have any hydrogen bonding or anything over there. Because hydrogen bonding is actually stabilizing it, right? When you heat it, you're giving it enough energy so that you can go and break those bonds. Because entropically over here, you're losing some energy, but enthalpically, you're getting some energy. So that is why the delta G is negative to form a such structured structure in alpha helix or beta sheet. But in random coil, you have a huge entropy. So that is the favorable thing, but there is no hydrogen bonding or anything to enthalpically help it. Delta H is pretty actually non-existent over here. However, at high temperature, you're giving enough energy from the outside. So only entropy can take care of the delta G. And you have to have enough enough energy coming from outside so that you can break these bonds and over their delta H. So from there, you can even find out what is the hydrogen bonding energy present in the alpha helix or beta sheet. Okay. And in some proteins, it might happen you have 5 alpha helices, 2 beta sheet. When you heat it, only 2 of them breaks down, not all of them. And from the CD spectra, you can find it out exactly which of them are actually breaking down. Okay, so there are all different kinds of possibilities out there. The main point is that from the CD spectra, you can follow it. Like what is the change happening by following the alpha helix, beta sheet, and random coil signatures. Okay, because this particular data I just showed over there, they are signature. No matter what, where you measure, a alpha helix always will show this particular peaks. Beta sheet will always show this particular peaks. Okay. Any more question?
Sir, I didn't get about the peak that is near 125, positive peak.
These are 125.
Sorry, 195.
195. So what do you mean? So what is the question? 195. So there is actually positive signal. So that means over here, this is AL minus AR, right? A function of that. That means over here, AL minus AR is a positive number. So that means your absorbance of the left-hand circular porous light is more than the right-hand circular porous light. And then you when come to 208, 222 around this region, AL is actually absorbed less compared to the right-hand circular porous light. So that is, it becomes negative. So that is what we mean by positive and negative. That is the direction of the value of the psi.
Thank you, sir.
Okay. Any more question, anyone?
Yes, sir. Sir, from that value, how can we decide that that is for the alpha helix or beta sheet? Means how we confirm that means that value. But I want to know that how is the characteristics is decided from that value.
Which value?
Sir, means that for the alpha helix it is decided that 193, or we will get that. But how will confirm that that is due to the alpha helix only, or when the first time is done, how will get that the alpha helix due
so
to
mainly people actually look into this negative region, to be honest, because this 208, 222, there are very unique 2 humps. Beta sheet have a very broad peak and random coil is in the positive side. So people mostly look into this region, 200 to 230 region. And over there, you have a result like this. And then you try to deconvolute it. Put different values for alpha helix and beta sheet and see which data by calculation is matching the original data. And from there, you can calculate like what is the probable alpha helix and beta sheet distribution for that particular protein. Does it answer your question, Arko? For an example, For example, if you take 70% alpha helix and 30% beta sheet versus a 50% alpha helix, 50% beta sheet, the overall data will not look same, because these three different humps, because there are three different humps when both alpha and beta helix are present, 208, 218, 222, and their contributions will vary with respect to the overall presence of the alpha helix and beta sheet. And that is what we actually follow. That what is the distribution of these three different humps at 208, 220, 218 and 222, and try to match it how it matches with the actual experiment. And from there we find out how it actually happens.